This recording will explain to you how to apply the Hopital's rule to find the limits of indeterminate forms. What are the meaning of indeterminate forms? In particular, I will be focusing on the type 0 over 0 in this recording. Suppose I want to find the limits of fx over gx as x approaching a. And if the limit of f of x when x approaching a is 0 and limit of g of x when x approaching a is also 0, then you have this situation of 0 over 0 case. This is what I mean the indeterminate form of the type 0 over 0. And what is 0 over 0? If you try to press a calculator, say 0 divided by 0, you are going to get error. And you also cannot do cancellation. You cannot say, oh, 0 cancel with 0 and then the answer is 1. This is not true. What are the examples where you encounter this indeterminate form? Examples: x squared minus 1 over x plus 1 and x approaching 1. Then, if you look at 1 squared minus 1, you get 0, and 1 minus 1 also 0. So this will give you actually a 0 over 0 form. But what is the actual answer? Actual answer, you can find the limit by x squared minus 1 by factorizing x plus 1, x minus 1. Now because x approaching 1, but x not equal to 1, you can cancel x minus 1. And then you find the limit of x plus 1 when x approaching 1, that is equal to 2. For the second case, sine x over x, we know that sine of 0 is 0. When x equals 0, you also have 0. Therefore, you again have a 0 over 0 case. But we know sine x over x when x approaching 0 is 1. Finally, 1 minus cosine x over x when x approaching 0. Cosine 0 is 1. We know that 1 minus cosine 0 is equal to 1 minus 1 equal to 0. And therefore, you have a 0 over 0 case again. We already know beforehand 1 minus cosine x over x when x approaching 0, the limit is 0. And the second and third result, you should memorize it. Here is the statement of Hopital's rule based on Howard Anton's text. This is for the form of 0 over 0. Suppose the function f and g are differentiable functions on an open interval containing the point x equal to a, except possibly at x equal to a, and that the limit of f of x when x approaching a is 0, and limit of g of x when x approaching a is also 0. If the limit of f prime x over g prime x exists, if this limit is plus infinity or minus infinity, then limit of fx over gx when x approaching a is the same as limit of f prime x over g prime x when x approaching a. Moreover, this statement is also true in the case of a limit when x approaching a minus, x approaching a plus, or x goes to minus infinity, or x goes to plus infinity. Let's look at example 1 taken from Howard Anton. We are going to find the limit of x squared minus 4 over x minus 2 when x approaching 2. This is of the form of fx over gx when x approaching 2, when f of x is x squared minus 4, g of x is x minus 2. Now we notice that f2 is equal to 2 squared minus 4 is 0. And g2 is 2 minus 2 is also 0. Therefore, we are actually having an indeterminate form 0 over 0 case. And we also know that fx and gx are both polynomial, so they are continuous at the point x equal to 2 and also both are differentiable at the point 2. Therefore, by using the Hopital rule, this is equal to limit of x goes to 2 differentiation of x squared minus 4 over differentiation of x minus 2. But we know by using the power rule, differentiate x power 2, we get 2x, and differentiation of x is 1. Differentiation of constant like 4 is 0. Differentiation of 2 is also 0. So the answer will be limit of x goes to 2, 2x over 1. And when x approaching 2, the limit is 4. Let's look at example 2a. I'm going to find the limit of sine 2x over x when x approaching 0. So this is the kind of limit fx over gx when x approaching 0, where fx is sine 2x and gx is x. And if we evaluate the function, I have f of 0 equal to sine 0, which is 0, and g of 0 is also 0. So we are getting a indeterminate form 0 over 0. And we know that f of x, g of x are continuous at the point x equals 0, and both are differentiable at the point x equals 0. Therefore, all the conditions required by the Hopital's rule are satisfied. And so the limit we find is equal to the limit of x goes to 0, differentiation of sine 2x over differentiation of x. And we know that differentiation of sine 2x is equal to cosine 2x first, and then you differentiate 2x using the chain rule, and this will give you 2 cosine 2x. And we know differentiation of x is 1. So the answer will be limit of x goes to 0, 2 cosine 2x over 1. When x approaching 0, I have denominator 2 cosine 0, denominator is 1, and we know cosine 0 is 1. So this 2 times 1 over 1 is 2. Let's look at example 2b. I have 1 minus sine x over cosine x when x approaching pi over 2. So this is the form of fx over gx when x approaching pi over 2, where my f of x is equal to 1 minus sine x and g of x equal to cos x. Now evaluate the function at the point pi over 2. F of pi over 2 will be 1 minus sine pi over 2, and we know sine pi over 2 is 1. You get 1 minus 1 equals 0. And g at the point pi over 2, we know is cosine pi over 2, and cosine pi over 2 is again 0. So again, we get an indeterminate form, 0, 0 over 0 again. Now both functions f and g are continuous at the point pi over 2. Now both are differentiable at the point pi over 2. So according to the Hopital's rule, this is equal to limit of x goes to pi over 2, differentiate 1 minus sine x over differentiate cosine x. And we know differentiate sine x is cosine x, differentiate cosine x, negative sine x, and differentiate 1, you get 0. We'll have the answer as the limit of x goes to pi over 2, 0 minus cosine x over negative sine x, and you put x equal to pi over 2, you have minus cosine pi over 2 and minus sine pi over 2 in the denominator, and we know cosine pi over 2 is 0 and sine pi over 2 is 1, and you have 0 minus 1, that will give me 0 as the answer. Let's look at example 2c in our Anton text. I'm going to find the limit of e power x minus 1 over x power 3 when x approaching 0. This is the type of the limit of fx over gx when x approaching 0. When f of x is e power x minus 1, g of x is x cubed. Now evaluate a function at the point 0. I get f0 equal to e power 0 minus 1, which is 1 minus 1 and equal to 0. And g of 0 is 0 power 3, which is also 0. Therefore, you are having an indeterminate form 0 over 0 case now. As we know that the function e power x minus 1 and x cubed are continuous at the point 0 and differentiable at the point x equals 0 by using the Hopital's rule. This is limit of x goes to 0, differentiation of e power x minus 1 over differentiation of x cubed. But we know differentiation of e power x will give you e power x. Differentiation of 1 is 0. Differentiation of x cubed is 3x squared. And this will give us the answer as limit of x goes to 0, e power x over 3x squared. Now as x approaching 0, we know that e power 0 is 1, and since the numerator is positive and denominator will be very near 0 and positive, so this is equal to infinity because you are having the situation of 1 over 0 plus, as we know that x squared is always positive, and when x goes to 0, 3x squared goes to 0 as well, but positive. So e power x over 3x will become 1 over 0 plus, and that will give me infinity, and that is why the answer is infinity now. Let's look at example 2d. Tangent x over x squared when x goes to 0 minus. That means that x approaching 0 from the left. So this is a situation. I have fx over gx when x goes to 0 minus. Fx is tangent x, gx is x squared. Now when x approaching 0 on the left, we know that f0, this tangent 0, we know is 0, g0, 0 square is also 0. So we are getting a indeterminate form 0 over 0. But f and g are continuous at the point x equals 0, and both are differentiable at the point x equals 0. So using the Hopital's rule, this is the limit of x goes to 0 minus, and differentiation of tangent x over differentiation of x squared. And we know differentiation of tangent x is secant square x, and differentiation of x squared is 2x. So putting this is equal to limit of x equal to 0 minus secant square x over 2x. Now when x approaching 0, secant square x approaching 1. Secant square 0 we know is 1, and 2 times 0 minus will be 0 minus. So you have a situation of 1 on the numerator, 0 negative, which is a very small number, but near 0 but negative. And the result for this ratio will be negative infinity. This is the end of this recording.